Right now, NASA's Swift Observatory and the European Space Agency's ground-based network are watching interstellar comet 3I Atlas C2025N1 exhibit non-gravitational acceleration that contradicts every standard model of cometary outgassing, leaving planetary scientists around the world profoundly unsettled. The numbers arrived November 6th, uploaded to NASA's secure data repositories shortly after midnight Universal Time. Radial acceleration 135 kilometers per day squared. Transverse component 60 kilometers per day squared. To put that in perspective, this visitor from another star system is gaining speed, sideways, at a rate equivalent to a car accelerating from 0 to highway speed over the course of 3 weeks, without any visible engine. The comet passed perihelion, its closest solar approach, on October 30th. Standard physics says it should be slowing down now, coasting outward on a ballistic arc shaped purely by the sun's gravity and the gentle pressure of sunlight. Instead, something is pushing it hard. Here's the problem. When comets heat up near the sun, frozen volatiles, water, carbon dioxide, methane, vaporize and jet outward, creating the iconic tail and imparting a tiny rocket effect. Astronomers have modeled this for decades. The models work. They worked for Halley, for Hale-Bopp, for every periodic comet ever tracked. They worked until 3I Atlas. The acceleration vectors don't match the observed coma geometry. The thrust is too strong, too asymmetric, and, most unnerving, there is no tail. NASA and ESA released coordinated statements on November 6th, each careful to emphasize ongoing analysis. Dr. Emily Kramer, a cometologist at NASA's Jet Propulsion Laboratory, framed it cautiously. We're seeing outgassing signatures in the spectral data, cyanogen, ammonia, traces of water vapor, but the distribution doesn't align with the acceleration profile. Normally, jets erupt from localized active regions on the nucleus, and we can trace them. Here, the coma is symmetric, almost perfectly symmetric. That symmetry, combined with this magnitude of non-gravitational force, is difficult to reconcile. Stop and consider that. A symmetric coma means gas is venting evenly from all sides, like a sphere slowly deflating. That should produce negligible net thrust. If the comet spins, any jets cancel out over a rotation. Yet 3I Atlas is accelerating as though a focused nozzle is firing from one hemisphere. The data say two contradictory things are happening at once. Dr. Marco Micheli, a near-Earth object specialist at ESA's NEOCC in Italy, ran the orbital integrations himself. He fed in positional measurements from 6 observatories spanning 3 continents, cross-checked them against archived images from late October, and computed the trajectory with and without the anomalous acceleration. The difference is stark. Without accounting for this mysterious thrust, 3I Atlas should have been 14,000 kilometers away from where it actually appeared on November 5th. That's not a rounding error. That's a comet behaving as though an invisible hand nudged it off course. Here's where it gets interesting. This is not the first time. In 2017, the interstellar object 1I Oumuamua tumbled through the inner solar system and exhibited a small, unexplained acceleration as it departed. The scientific community debated for months. Outgassing was the leading natural explanation, but Oumuamua showed no coma, no tail, no spectroscopic evidence of volatile release. Some researchers proposed exotic ice compositions, hydrogen icebergs, nitrogen slabs, that might vent gas invisibly. Others, notably Harvard astrophysicist Avi Loeb, raised the possibility of artificial origins, a light sail, a derelict probe, a piece of interstellar technology adrift. The controversy never fully resolved. Oumuamua faded from view before definitive observations could be made. Now 3I Atlas has arrived, and the parallels are impossible to ignore. Loeb, reached by email on November 7th, did not mince words. The lack of a tail combined with this unexplained push screams, not your average comet, perhaps an alien artifact on a reconnaissance mission. We've seen this pattern before. If it walks like a duck twice, maybe it's time to seriously consider ducks. NASA predictably pushed back. In a terse update issued November 6th, the agency reiterated that natural degassing remains the most plausible explanation, and that additional high-resolution imaging from the Mars Reconnaissance Orbiter's HiRISE camera is pending, though delays caused by the current U.S. government shutdown have slowed data processing. Read between the lines, NASA is hedging, ESA is hedging. No one wants to be the institution that prematurely declares comet behaves oddly and later gets proven wrong by an overlooked detail in the thermodynamics. But equally, no one wants to dismiss an anomaly that might rewrite textbooks. The tension is palpable in every carefully worded press release, every hedged quote, every ongoing analysis disclaimer. Now about the data. The acceleration itself breaks down into two components: radial, pointing directly away from the Sun, and transverse, perpendicular to that line. The radial component, 135.5 km day², could in principle be explained by outgassing if the comet were shedding mass rapidly. The calculations suggest it might be losing up to 13% of its total mass through volatile ejection. 13%. Think about what that means. If 3I Atlas has a nucleus a few hundred meters across, composed of ice and rock, it's vaporizing thousands of tons of material every day. For a small body, that's catastrophic. Comets can fragment under such stress, yet multiple imaging campaigns from November 6 and 7 show no signs of fragmentation. The nucleus remains intact, compact, shrouded in that eerily symmetric coma. The transverse component, 60 km day², is harder to explain. Transverse acceleration implies the thrust isn't aligned with the Sun-comet axis. Something is pushing the comet sideways. Outgassing can produce transverse forces if the nucleus is rotating and jets fire at an angle, creating a torque and a net sideways kick over time. But again, that requires asymmetric jetting, which should produce an asymmetric coma and a tail. The observations show neither. Dr. Kasper Wierschos, an astronomer at the Catalina Sky Survey in Arizona, captured 3I Atlas on November 5th using a 1.5-meter telescope. His images, released publicly on November 6th, reveal a bright, star-like nucleus surrounded by a diffuse circular envelope glowing faintly blue-green. Spectroscopic analysis by the Gemini Observatory confirmed emissions from cyanogen, CN, and ammonia, NH3, both common cometary volatiles. The Swift Observatory, NASA's ultraviolet space telescope, detected hydroxyl radicals, OH, and faint signatures consistent with water vapor plus organic molecules, glycine, an amino acid, and hydrogen cyanide. These are the chemical fingerprints of life's building blocks, the same ingredients found in meteorites and in the cold molecular clouds where stars are born. But here's where things get strange. Cyanogen gives comets that greenish hue, a well-documented phenomenon. Ammonia is rarer but not unheard of, especially in comets originating from the outer solar system or beyond. What stands out is the ratio. The CN to OH ratio in 3I Atlas is skewed higher than typical solar system comets, suggesting a different formation environment, a different primordial ice reservoir. If this comet formed around another star, a cooler star perhaps, or in a disk richer in nitrogen compounds, its chemistry would reflect that alien origin. The presence of glycine is tantalizing. Glycine has been found in comet samples returned by the Stardust mission and in meteorites, so it's not unprecedented. But in an object demonstrably from another stellar system, it raises immediate questions about the universality of prebiotic chemistry. Did glycine form in 3I Atlas's home system the same way it forms here? Does that imply similar planetary formation processes? Similar possibilities for life? Dr. Clara Sousa Silva, a molecular astrophysicist at the Harvard-Smithsonian Center for Astrophysics, studies exotic molecules in space. Contacted for comment, she offered measured enthusiasm. Finding amino acids in an interstellar comet is like receiving a postcard from another solar system's chemistry lab. It tells us that the basic organic inventory isn't unique to our neighborhood. But we have to be careful. Glycine is relatively simple, and hydrogen cyanide is a common precursor in space. The real question is whether 3I Atlas also carries more complex molecules, peptides, sugars, that would suggest active prebiotic processes wherever it came from. Think about what that means. If interstellar comets routinely transport organic molecules between star systems, they could be vectors of panspermia on a galactic scale. Life, or at least its chemical ingredients, might not arise in isolation. It might be seeded, shared, distributed by icy wanderers like 3I Atlas drifting through the void for millions of years, carrying frozen archives of their birth clouds. Earth's own oceans and organic matter might trace back in part to ancient cometary impacts. If 3I Atlas came from a system where planets formed and chemistry evolved, could it also carry dormant microbes, locked in ice, awaiting a warm world to thaw them? NASA has not speculated publicly on exobiology, but SETI, the search for extraterrestrial intelligence, has. On November 6th, the SETI Institute's Allen Telescope Array in California began scanning 3I Atlas across a broad radio spectrum, searching for any artificial signals, narrowband transmissions, pulsed beacons, anything that might indicate technology. As of November 7th, the scans have detected nothing. Silence. Dr. Andrew Siemian, principal investigator for the Breakthrough Listen initiative, acknowledged the null result but emphasized the search continues. Absence of evidence is not evidence of absence. If there's any chance this object is artificial, or even if it's natural but being tracked by another civilization, we'd be remiss not to listen. Our sensitivity is improving daily. The idea that 3I Atlas could be artificial is not as fringe as it once seemed. Oumuamua forced that conversation into mainstream astrophysics. Loeb, in his 2021 book and numerous papers, argued that the scientific method demands considering all hypotheses that fit the data, including non-natural origins, and then testing them. The hypothesis that 3I Atlas is a probe, whether active, dormant, or derelict, fits some of the data. An artificial object could exhibit non-gravitational acceleration via propulsion, attitude control thrusters, or even a malfunctioning drive system. It could lack a tail if it's not shedding ice but venting fuel or coolant. The symmetric coma could be a shroud of outgassed material from a slow leak, evenly distributed by gentle rotation. Here's the problem with the artificial hypothesis. It requires extraordinary evidence, and so far the evidence is merely unusual, not extraordinary. No one has detected radio signals. No one has imaged surface structures inconsistent with a natural nucleus. The spectroscopy shows molecules expected in comets, not industrial byproducts. The orbit, while hyperbolic, confirming interstellar origin, doesn't suggest powered flight. It's consistent with an object flung out of another star system by gravitational interactions millions of years ago, now drifting on a ballistic trajectory perturbed only slightly by the sun's gravity and that mysterious acceleration. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury in New Zealand, argues for caution. We've observed fewer than a dozen interstellar objects ever. Our sample size is laughably small. We don't yet know what normal looks like for these visitors. Maybe strong outgassing and weird acceleration are common. Maybe symmetric comas are typical for objects formed in different protoplanetary disks. Jumping to alien probe before exhausting natural explanations is scientifically premature. Yet the natural explanations are struggling. Several teams have proposed models. One idea: the nucleus is spinning rapidly, and subsurface ice reservoirs are venting through fissures that happen to be symmetrically distributed, producing a net thrust that averages out to look like a radial and transverse push. But rapid spin should cause the nucleus to elongate or fragment over time, and 3I Atlas appears stable. Another idea: the surface is coated with a dark, insulating lag deposit, dust and organic gunk that traps heat and causes violent subsurface sublimation, ejecting gas in unpredictable bursts. This could explain asymmetric thrust without a visible tail if the dust absorbs the escaping gas before it becomes luminous. But the spectroscopy clearly shows gas emissions glowing in the coma, so the gas is escaping into space, not being absorbed. A third, more exotic model invokes supervolatiles, substances like carbon monoxide or nitrogen that vaporize at extremely low temperatures far from the sun. If 3I Atlas is rich in these ices, it could have started outgassing well beyond the orbit of Mars, sustaining thrust over a longer period than water-dominated comets. The trouble is, CO and N2 are difficult to detect spectroscopically unless present in large quantities, and they don't produce the blue-green coma observed. The cyanogen and ammonia signatures dominate, suggesting more conventional volatiles. Dr. Davide Farnocchia, a navigation engineer at JPL who computed the non-gravitational acceleration, ran sensitivity tests. He varied the assumed mass, rotation period, and surface properties of 3I Atlas within plausible ranges and recalculated the expected outgassing forces. In most scenarios, the models undershoot the observed acceleration by a factor of 2 or more. To match the data, he had to assume either an implausibly low nucleus mass, making the object more fragile than any known comet, or an implausibly high outgassing rate that should have exhausted the volatile reservoir days ago. Neither assumption is physically comfortable. Stop and consider that. The math doesn't close. The observations are solid. Dozens of telescopes, consistent positional data, verified spectroscopy. The physics is well tested. Newton's laws, thermodynamics, radiative transfer. Yet when combined, they don't produce the trajectory actually observed. Something is missing from the equation. Enter China's Tianwen-1 Mars orbiter. On the evening of November 6th, while stationed in Mars orbit approximately 1.2 astronomical units from 3I Atlas, Tianwen-1's high-resolution camera captured a sequence of images over a 6-hour window. The Chinese National Space Administration released the images publicly on November 7th. They corroborate earlier ground-based observations: no tail, a bright compact nucleus, a symmetric coma extending roughly 50,000 kilometers in diameter. But Tianwen-1 added a critical detail. The brightness of the nucleus varied over the observation period, dimming and brightening with a periodicity of approximately 4.7 hours. This is likely the rotation period. A rotating nucleus with an irregular shape would naturally show brightness variations as different surface areas, some more reflective, some darker, turn toward the observer. What makes this significant is that a 4.7-hour rotation is relatively fast for a comet. Faster rotation could amplify asymmetric outgassing effects, potentially explaining some of the transverse acceleration. But it also places mechanical stress on the nucleus. If 3I Atlas is a loosely bound rubble pile, as many comets are, a 4.7-hour spin could be close to the breakup limit. The fact that it hasn't disintegrated suggests either a more cohesive internal structure, perhaps a monolithic chunk of ice, rather than a rubble pile, or that the outgassing is somehow stabilizing the rotation, a feedback loop not fully understood. Cross-referencing Tianwen-1 data with imagery from NASA's Parker Solar Probe, ESA's ExoMars Trace Gas Orbiter, and Mars Express revealed another anomaly: a 5-fold brightness spike in green wavelengths between November 5th and November 6th, without corresponding increases in other colors. Green emission in comets typically comes from diatomic carbon, C2, or cyanogen. A sudden spike implies a surge in production of these molecules, possibly triggered by the exposure of a fresh ice patch as the surface eroded, or by a transient heating event. But transient heating should affect all volatiles, producing a multicolor brightness increase. The selective green spike is odd. Dr. Cyrielle Opatom, a cometary scientist at the University of Edinburgh, reviewed the multi-wavelength light curves and proposed a scenario. If a subsurface pocket of cyanogen-rich ice suddenly breached the surface, perhaps due to thermal fracturing or a small impact from debris, it would flash vaporize in the sunlight, creating a brief, intense emission in the CN bands. That could explain the green spike, but the timing is curious. It happened right as multiple spacecraft were watching. Coincidence? Or did something trigger it? Read between the lines. Coincidence? Or did something trigger it? Scientists don't usually phrase questions that way unless they're entertaining possibilities they can't yet articulate in a formal hypothesis. What could trigger a subsurface eruption? Internal heat from radioactive decay is negligible in a small comet. Tidal stress from the sun is minimal at 1.2 AU. An impact seems improbable given the vastness of space. That leaves either a spontaneous structural failure, ice cliffs collapsing, internal voids collapsing, or something more deliberate. Here's where it gets interesting. If 3I Atlas were artificial, or even partially artificial, a natural nucleus retrofitted with instrumentation, a derelict probe encased in ice, a sudden power surge, a venting of stored propellant, or the activation of a dormant system could produce an outgassing event. Far-fetched? Absolutely. But the data are strange enough that even far-fetched ideas warrant at least a thought experiment. Think about what that means if taken seriously. An interstellar probe designed to study star systems might use a stealth approach, coat itself in ice, mimic a comet, pass through the inner system gathering data, then depart. The ice provides radiation shielding, thermal buffering, and camouflage. Occasional venting adjusts trajectory without revealing obvious propulsion. The lack of radio signals could be intentional. Why broadcast if the goal is reconnaissance? The organic molecules detected could be contamination from the probe's origin world, or even deliberate seeding, a form of directed panspermia. This speculation is, of course, far beyond the current evidence. No reputable institution is officially endorsing the probe hypothesis. But privately, in emails and Slack channels among planetary scientists, the discussions are less guarded. One senior astronomer, speaking on condition of anonymity, summarized the mood. We're in a strange position. The data are weird, but not definitive. If we scream aliens, we get mocked and defunded. If we ignore the weirdness, we might miss the discovery of the millennium. So we do science. We gather more data, we test models, we wait for the anomaly to either resolve into something mundane or escalate into something undeniable. The broader implications ripple outward. If 3I Atlas is natural but represents a new class of interstellar comet with unexpected properties, that reshapes models of planetary system formation and dynamical evolution. It means our theories, derived from solar system comets, are parochial, incomplete. It means the galaxy is more diverse chemically and physically than the local sample suggested. If 3I Atlas is artificial, the implications are existential. It confirms we are not alone. It implies a technological civilization advanced enough for interstellar travel, or at least interstellar probes. It raises immediate questions. Who built it? When? Why? And are they still out there? Is 3I Atlas one of thousands of such probes drifting through the galaxy, a network of exploration, or a singular relic from a long-dead civilization? Either way, humanity's place in the cosmos shifts. The discovery of even microbial life beyond Earth would be transformative. The discovery of evidence, however circumstantial, of extraterrestrial technology would be revolutionary. Funding agencies would be forced to take astrobiology and SETI seriously. Space missions would pivot toward intercept and rendezvous with future interstellar objects. Philosophies, religions, geopolitics, all would feel the tremor. But that is speculative extrapolation. Right now, on November 7, 2025, the situation is simpler and more frustrating. 3I Atlas is accelerating, and no one is entirely sure why. What comes next depends on observation campaigns already underway, and those being rapidly organized. The James Webb Space Telescope, NASA's flagship infrared observatory, was originally scheduled to observe 3I Atlas on November 10th. But the government shutdown has thrown scheduling into chaos. If JWST can be tasked, its sensitivity could detect faint molecular emissions missed by ground-based telescopes, constraining the composition and outgassing rate. The European Southern Observatory's Very Large Telescope in Chile has dedicated time on November 8th and 9th for high-resolution spectroscopy, aiming to map the comet's chemical gradient and search for jets or asymmetries at sub-arc-second scales. The Mars Reconnaissance Orbiter's HiRISE camera, capable of resolving surface details as small as a meter across on Mars, could theoretically image 3I Atlas's nucleus if pointed correctly, despite the distance. NASA requested targeting on November 6th, but data processing delays mean results may not arrive until mid-November. If HiRISE captures the nucleus, scientists will scrutinize every pixel for shapes, textures, reflectivity variations, anything inconsistent with a natural ice and rock body. Amateur astronomers are contributing too. 3I Atlas is currently visible in the pre-dawn sky near the constellation Virgo, glowing at roughly 10th magnitude, too faint for the naked eye but accessible to backyard telescopes of 6 inches aperture or larger. Thousands of observations from amateur networks are being compiled by the American Association of Variable Star Observers and the International Astronomical Union's Minor Planet Center, providing additional positional data to refine the orbit and monitor brightness fluctuations. On December 19th, 3I Atlas will make its closest approach to Earth, passing at a safe distance of 1.8 astronomical units, roughly 270 million kilometers farther than the Sun. Even at closest approach, it will remain a telescopic target, not a naked eye spectacle. But that proximity offers a final opportunity for intensive study before the comet recedes into the outer solar system and eventually back into interstellar space. Radio observatories, including the Arecibo Successor Facilities and the Square Kilometer Array Pathfinders, are planning coordinated campaigns to search for any emissions, natural or artificial, across a wide frequency range. Dr. Frank Marcius, senior planetary astronomer at the SETI Institute, outlined the timeline. We have a narrow window. By early December, 3I Atlas will be too faint for most ground-based spectroscopy. The December 19th flyby is our last good chance for high-signal observations. After that, it fades fast. If we're going to answer the big questions, composition, structure, the source of the acceleration, we need every telescope we can muster pointed at this thing for the next month. The financial and logistical pressures are immense. Telescope time is precious, allocated months in advance through competitive proposals. Repointing major observatories on short notice to chase a transient target disrupts scheduled programs, frustrates other researchers, and requires high-level justifications. Yet the scientific community has rallied. The International Astronomical Union issued a circular on November 6th encouraging global cooperation. ESA and NASA have publicly committed resources. Even rival space agencies, Roscosmos, CNSA, ISRO, have expressed willingness to share data. The comet, in a sense, is uniting the fragmented landscape of space science, at least temporarily. But unity brings its own tension. Who interprets the data? Who gets to make the first announcement if something definitive emerges? In 2017, the Oumuamua discoveries were marred by rushed press releases, contradictory papers, and priority disputes. Lessons were learned. This time, a working group coordinated by the IAU's Division F, Planetary Systems and Bioastronomy, is aggregating observations and vetting interpretations before public release. The goal is to avoid sensationalism while maintaining transparency. It's a delicate balance, and not everyone is satisfied. Loeb, for instance, has criticized what he perceives as institutional conservatism, a reluctance to publicly entertain non-standard explanations even when the data warrant it. He wrote in a November 7th blog post, "Science advances by challenging assumptions, not by clinging to them. If the evidence points towards something extraordinary, our obligation is to investigate rigorously, not to suppress discussion out of fear of controversy. The history of astronomy is littered with missed opportunities because observations were dismissed as instrumental errors or anomalies unworthy of follow-up. Let's not repeat that mistake." His words resonated widely, shared thousands of times across social media, sparking both support and backlash. Critics accuse him of grandstanding, of leveraging ambiguous data to promote speculative ideas. Supporters argue he's simply doing what scientists should do, following the evidence wherever it leads, even into uncomfortable territory. The truth, as always, is complex. Loeb's hypothesis that Oumuamua might be artificial was scientifically legitimate. It made testable predictions, could be falsified, and addressed observational anomalies. But it was also low probability, requiring assumptions about alien technology and motivations for which there is no independent evidence. The same applies to 3I Atlas. The probe hypothesis is plausible in the narrow sense that it's not physically impossible, but it's not the simplest explanation. Occam's razor, the principle that simpler explanations should be preferred absent compelling evidence, sans santuquinge, still favors natural processes. Yet Occam's razor is a heuristic, not a law. Nature is not obligated to be simple. And the history of science includes moments when the simpler, more comfortable explanation turned out to be wrong. Continental drift was once dismissed as implausible. The Big Bang was initially mocked. Exoplanets were theoretical speculation until the first detections in the 1990s. Humility demands acknowledging that our current understanding, however robust, is provisional. Dr. Sarah Seeger, a planetary scientist at MIT renowned for her work on exoplanet atmospheres, offered a nuanced take. We should be open-minded, but not credulous. Extraordinary claims require extraordinary evidence, yes, but we also have to be willing to recognize extraordinary evidence when it arrives. The challenge with 3I Atlas is that the evidence is peculiar, not yet extraordinary. It's a puzzle, possibly a major one. We owe it to ourselves to solve the puzzle rather than prematurely declaring either it's just a comet or it's aliens. Both are intellectual shortcuts. The real work is in the details. The details are accumulating fast. On November 7th, spectroscopic observations from the Gemini North Telescope in Hawaii detected a faint emission line at 3.4 micrometers, consistent with organic carbon-hydrogen bonds, possibly polycyclic aromatic hydrocarbons, PAHs. PAHs are common in space, found in interstellar dust, meteorites, and comets. But the strength of the 3.4 micrometer feature in 3I Atlas is stronger than expected for a typical comet, suggesting a higher abundance of complex organics. This ties back to the glycine detection. Perhaps 3I Atlas formed in an unusually carbon-rich environment, a molecular cloud seeded by the death throes of a massive star, rich in the organic detritus of stellar nucleosynthesis. Dr. Sun Kwok, an astrobiologist at the University of Hong Kong, has long argued that complex organic molecules, including the precursors to life, are widespread in the galaxy, synthesized in stellar outflows, and distributed by interstellar dust and comets. He sees 3I Atlas as vindication. This is exactly what we'd expect if organic chemistry is a universal outcome of stellar and planetary processes. An interstellar comet should be a treasure trove of prebiotic compounds. The question is whether those compounds ever gave rise to life in their home system, or whether they're still waiting for the right conditions. That question may never be answerable for 3I Atlas. Even if we intercept it with a spacecraft, a mission that would take years to plan and launch and return samples, detecting extinct life or biochemical signatures from another world is extraordinarily difficult. Life leaves subtle marks, isotopic fractionations, chiral asymmetries in organic molecules, microfossils. But those marks degrade over time, especially in the harsh environment of space. Still, the possibility electrifies astrobiologists. NASA's Planetary Defense Coordination Office has been monitoring 3I Atlas, not because it poses a threat, it doesn't, but because interstellar objects offer unique opportunities for planetary defense research. Understanding their composition and structural integrity informs models of what would happen if a future interstellar object were on a collision course with Earth. Dr. Lindley Johnson, Planetary Defense Officer Emeritus, noted, "Every interstellar visitor is a free sample delivery from another star. We learn about building materials, ice composition, tensile strength. If we ever need to deflect one, that knowledge could be critical. Plus, in the farther future, if humanity expands into the solar system and beyond, knowing how to identify and utilize resources from interstellar objects could be valuable. Utilization is a distant prospect but not absurd. An interstellar comet is a cold, slow-moving reservoir of water and organic molecules. If intercept missions become feasible, such objects could be mined for propellant or raw materials. There's even speculative discussion, decades premature, of using interstellar objects as stepping stones for exploration, hitching rides on their hyperbolic trajectories to reach the outer solar system or even interstellar space more quickly than conventional propulsion allows. But all of that is contingent on understanding what 3I Atlas actually is. And right now, November 7th, the understanding is incomplete. Here's where things get strange. At 14:23 UTC on November 7th, the Zwicky Transient Facility, ZTF, a robotic survey telescope in California designed to scan the sky for transient events, captured 3I Atlas during a routine field observation. The automated pipeline flagged an unusual photometric event, a brief 11-second brightening by approximately 0.3 magnitudes, followed by a return to baseline. 11 seconds is far too short for standard cometary outbursts, which typically last minutes to hours. It's more consistent with a glint, a specular reflection from a flat, shiny surface rotating into view. Glints are well documented in artificial satellites. Sunlight reflects off solar panels or polished metal, causing a brief flash. But comets are irregular, dusty, rough-textured. They don't produce glints. Ice facets, in principle, could reflect sunlight, but cometary ice is typically mixed with dust and organics, creating a diffuse, matte surface. A clean, mirror-like ice patch is theoretically possible if freshly exposed, but would dirty quickly as surrounding dust settles. The ZTF detection has not yet been peer-reviewed or independently confirmed. It could be an instrumental artifact, a cosmic ray hit mice identified by the software, or a background star that happened to align with 3I Atlas in that moment. But it could also be real. If real, it demands explanation. Dr. Eric Christensen, principal investigator of the Catalina Sky Survey, reviewed the ZTF data at the request of colleagues. His assessment: the event is marginally significant, right at the edge of our detection confidence. I wouldn't bet my career on it being real, but I wouldn't dismiss it either. If other surveys caught the same thing, that would be compelling. Right now, it's a tantalizing maybe. A tantalizing maybe. That phrase encapsulates the entire 3I Atlas situation. Every new observation adds a piece to the puzzle, but the pieces don't yet form a coherent picture. Instead, they form a mosaic of maybes. Maybe natural, maybe exotic, maybe unprecedented, maybe mundane. The uncertainty is maddening for scientists trained to converge on answers and exhilarating for those who thrive on mystery. Public interest has surged. News outlets from the New York Times to the BBC have run features on 3i Atlas, often emphasizing the alien probe angle because it attracts clicks, even as the reporters dutifully note that scientists urge caution. Social media is awash with speculation, memes, and conspiracy theories. Some claim 3i Atlas is a precursor to alien contact, others that it's a natural comet being hyped for funding. A vocal minority insists it's a classified military project or a hoax. The noise-to-signal ratio is high, but buried in the noise are thoughtful threads by amateur astronomers, science educators, and informed enthusiasts who are genuinely grappling with the data and asking smart questions. One Reddit thread posed a question that gained traction. If 3i Atlas is a probe, why would it accelerate now so close to the Sun, where it's most visible? Wouldn't it make more sense to stay stealthy? The responses varied. Some suggested the acceleration is unavoidable, a consequence of thermal expansion or outgassing triggered by solar heating, whether the object is natural or artificial. Others proposed that if the object is a probe, the acceleration might be a course correction executed despite the risk of detection, implying the original trajectory was off target, or that a priority destination required the burn. A few entertained the idea that the acceleration is intentional signaling. We're here and we're not natural. That interpretation, while dramatic, lacks supporting evidence. Think about what that means if the acceleration were deliberate. A civilization capable of sending a probe across interstellar distances would presumably have fine control over its trajectory. Accelerating visibly in the inner solar system, where telescopes would notice, could be a way to announce presence without overt aggression. It's a hypothesis that fits the data no better or worse than natural outgassing, but it introduces assumptions about alien intent, communication strategies, and technological capabilities, all of which are speculative. Still, it's the kind of hypothesis that, once articulated, is hard to completely ignore. Dr. Jill Tarter, former director of SETI research and a pioneer in the search for extraterrestrial intelligence, weighed in during a radio interview on November 7th. We have to entertain all possibilities, but we also have to rank them by plausibility. A comet outgassing strangely is vastly more plausible than an alien probe, simply because we know comets exist and we've seen them do weird things before. We've never confirmed an alien probe. That doesn't mean it's impossible, just that the prior probability is low. However, low probability doesn't mean zero. If the data keep pointing in a strange direction, we adjust our probabilities. That's Bayesian reasoning. Right now, my credence in the probe hypothesis is maybe 1%. If we detect a radio signal or see geometric structures on the nucleus, that credence jumps. If we find a natural explanation for the acceleration, it drops to 0. We're in the information gathering phase. 1% is not nothing. In a universe with hundreds of billions of galaxies, each with hundreds of billions of stars, a 1% chance that any given anomaly is extraterrestrial technology still implies a non-negligible absolute probability of encountering such technology eventually. The question is whether 3i Atlas is that encounter or just another false alarm in a long series. The false alarms are numerous. Pulsars were briefly thought to be alien beacons when first discovered in 1967, until their natural origin as rotating neutron stars was established. Tabby's star, with its strange dimming patterns, sparked speculation about megastructures before dust, and debris emerged as more plausible explanations. Fast radio bursts were mysterious until models involving magnetars and neutron star collisions gained traction. Oumuamua remains contentious, but most researchers have moved on, accepting that it was likely natural even if not fully understood. The pattern is clear. Extraordinary claims rarely pan out, and the universe is filled with natural phenomena strange enough to mimic design. Yet the pattern is not absolute. Pulsars, quasars, black holes, all were once too bizarre to be believed, until observations forced acceptance. The universe is under no obligation to conform to human intuition. If interstellar probes exist, one will eventually be found. The challenge is distinguishing the true positive from the noise. So what would constitute definitive evidence? The scientific community has debated this extensively, particularly in the wake of Oumuamua. A consensus has emerged around several criteria. First, an artificial object should exhibit acceleration inconsistent with all plausible natural processes, not just poorly modeled ones. Second, it should show structural or compositional features incompatible with natural formation, geometric shapes, regular patterns, materials not found in nature. Third, it should emit signals, radio, optical, or otherwise, that are clearly artificial, narrowband, modulated, or information-rich. Fourth, ideally, it should be verified by multiple independent observations using different instruments and methods, ruling out instrumental artifacts. 3i Atlas meets the first criterion partially. The acceleration is anomalous, but not yet proven incompatible with exotic natural processes. It fails the second criterion. No structural anomalies have been confirmed. It fails the third. No signals detected. It meets the fourth. Multiple observatories have corroborated the basic observations. In summary, 3i Atlas is intriguing but not definitive. The coming weeks will be decisive. If high-rise images reveal something unexpected, surface regularity, reflective patches, angular features, the conversation shifts dramatically. If JWST spectroscopy finds molecules with no plausible natural source, industrial compounds, refined metals vaporizing from a hot surface, the game changes. If SETI detects a signal, even a faint one, the world wakes up. Conversely, if better outgassing models close the gap between prediction and observation, if the acceleration naturally decays as the comet cools, if every anomaly finds a mundane explanation, then 3i Atlas will be remembered as a fascinating but ultimately ordinary interstellar visitor, a testament to the diversity of comets and the limits of our models. The tension between these futures is what drives the urgency. Every astronomer involved knows they might be witnessing history or chasing a mirage. The difference won't be clear until the data are complete, and the data are never truly complete. At some point, a decision will be made. Enough evidence to conclude, or enough ambiguity to remain agnostic. That decision will be debated for years. Stop and consider that. The scientific process is often portrayed as dispassionate, algorithmic. Gather data, test hypotheses, reach conclusions. In practice, it's messier. Scientists are human, influenced by career incentives, peer pressure, funding realities, personal biases. A young researcher might avoid the alien probe hypothesis to protect their reputation. A senior scientist with tenure might embrace it, seeking a legacy-defining discovery. Journals might reject speculative papers or publish them depending on editorial whims and reviewer prejudices. The media amplifies controversy because it's compelling, distorting public perception. All of these forces shape which hypotheses get investigated and which get sidelined. The 3i Atlas investigation is occurring in this messy reality. Multiple teams are racing to publish, to claim credit, to shape the narrative. Collaborations are forming and fracturing. Data are being shared, hoarded, leaked. Rivalries simmer. Alliances shift. It's science as a human endeavor, competitive and collaborative, rigorous and flawed. But through the mess, the process works. Observations accumulate. Models improve. Errors are corrected. Consensus emerges, slowly, painfully, but eventually. The question is whether the consensus around 3i Atlas will be weird comet, cool science, or we need to rethink everything. Dr. Alan Stern, principal investigator of NASA's New Horizons mission to Pluto and beyond, has proposed a dedicated interstellar object interceptor mission. The concept, dubbed Bridge, would place a spacecraft on standby in a parking orbit, ready to launch on short notice when a new interstellar visitor is detected. Bridge could reach the object, perform a high-speed flyby or even rendezvous, and return close-up images, spectra, and particle samples. It's technically feasible with existing propulsion technology, though expensive and logistically challenging. As of November 7th, Bridge remains a concept, unfunded, but the existence of 3I Atlas has rekindled advocacy. Stern has been lobbying NASA and private space companies to greenlight development. We've now seen 3 interstellar objects in 8 years, Stern argued in a recent op-ed. The rate suggests we'll detect several per decade with improving survey telescopes. Each one is a unique scientific target, a free sample from another star system. We'd be foolish not to go take a close look. The cost of a fast turnaround mission is comparable to a flagship planetary mission, and the science return could be transformative. If even one of these objects turns out to be artificial, the return on investment is infinite. Infinite return? The language of exploration has always flirted with hyperbole, but in this case, it's not entirely unjustified. Confirming extraterrestrial technology would be the most significant scientific discovery in human history, dwarfing even the Copernican revolution or the structure of DNA. It would mean humanity is not the only technological species, that intelligence and engineering arise elsewhere, that the cosmos might be populated, even if sparsely, with minds and machines. The philosophical and practical ramifications would reverberate for generations, but that's speculation contingent on the probe hypothesis being true, which remains a long shot. More likely, 3I Atlas is a natural object with properties that stretch but do not break our current understanding of comets. If so, it's still valuable. Every anomaly, even if ultimately explained, teaches something. The hunt for an explanation drives innovation in modeling, observation, and theory. The process matters as much as the conclusion, and the process is ongoing. On November 7th, the Subaru telescope in Hawaii began a multi-night campaign to monitor 3I Atlas in visible and near-infrared wavelengths, tracking brightness variations and searching for spectral features that evolve as the nucleus rotates. The European Space Agency's Gaia mission, primarily a star mapping satellite, day², has been repurposed briefly to obtain precise astrometry of 3I Atlas, improving the orbit determination and potentially detecting subtle variations caused by outgassing torque. The Very Long Baseline Array, a continent-spanning network of radio telescopes, is attempting to detect any radio emissions, natural or artificial, with unprecedented sensitivity. Each of these efforts represents a commitment of time, money, and expertise. Each is a bet that 3I Atlas is worth the investment, and each will yield data, whether or not those data are sensational. Science is a long game, an accumulation of knowledge brick by brick, with occasional leaps when something truly unexpected emerges. So where does that leave us? On November 7, 2025, as the data pour in and the debates rage, we are watching an interstellar comet, a visitor from another star system, carrying the chemical and physical imprint of an alien environment, exhibit behavior that challenges standard models. It is accelerating in a manner inconsistent with simple outgassing, showing a symmetric coma without a tail, releasing organic molecules including amino acids, and displaying transient brightness variations that defy easy explanation. Multiple independent observations from ground and space-based telescopes confirm the anomalies. Natural explanations exist but are strained, requiring assumptions that are uncomfortable, though not impossible. Artificial explanations are even more strained, requiring assumptions about alien civilizations for which we have no independent evidence. The scientific community is responding with appropriate rigor, gathering more data, refining models, testing hypotheses, maintaining skepticism while staying open to surprises. The public is engaged, alternately fascinated, and frustrated by the ambiguity. The media is oscillating between sober reporting and sensationalism, and 3i Atlas continues its journey, indifferent to the scrutiny, accelerating outward toward the stars, carrying its secrets, natural or otherwise, into the dark. Here's the final, suspenseful question, the one that lingers as the observations continue and the models churn. If the acceleration is real, if the symmetric coma and the missing tail are not artifacts or misunderstandings, if the organic molecules and the brightness spikes and the faint glint all represent genuine, reproducible phenomena. What does that imply about the object's nature? Is it merely a comet unlike any seen before, shaped by the alien conditions of a distant protoplanetary disk? A reminder that the galaxy is vast and diverse and full of surprises? Or is it something more, a traveler with purpose, a machine or artifact from another world, drifting through our system on an errand we can only guess at, leaving us to puzzle over its trail like ancient astronomers staring at a strange light in the sky? And if it is the latter, if somewhere in the assembly of ice and rock and organic haze, there lies an engineered core, a probe or relic from a civilization that mastered the stars, what does it mean that we are only now, in 2025, just beginning to notice? How many others have passed through undetected in the eons before we had telescopes and spectrographs? How many more will come? And how long until we're ready to truly understand what they are? The universe is old, far older than humanity. It has had time for countless civilizations to rise, spread, and perhaps fall. If even a fraction sent emissaries into the void, the galaxy might be crisscrossed with their silent messengers, adrift for millions of years, waiting for someone to look closely enough to see. 3i Atlas is accelerating away from the sun. In a few months, it will be gone, a fading point of light receding into the abyss. The window to answer these questions is narrow and closing. If we miss it, the mystery endures. If we solve it, the universe either stays familiar, wondrous but knowable, or it becomes suddenly, irrevocably larger, populated not just by stars and planets, but by the fingerprints of others who looked up and wondered and reached out. The data are coming in. The scientists are working. The telescopes are watching. And 3i Atlas, whatever it is, speeds silently on,